Okay, hello and welcome back everyone. So moving on to the next subsection, which is underneath the complex numbers section of the entire book. We're looking at the polar complex numbers today. So polar, as I hinted in the previous video, is the counterpart to a Cartesian coordinate system. And these are systems which describe a two-dimensional space. So think about the xy plane. Now let's recall really quick, the Cartesian coordinate system was built around 90 degrees axes. The polar coordinate system is going to be built around concentric rings as well as outward pointing rays. So we can think about a bunch of rays pointing outwards as well as concentric rings around these rays. And of course, this is where the word polar comes from. Let's say polar, like the top of a globe, as opposed to bottom to top or bottom of a globe. If you see the latitude or longitude lines looking from the North Pole, they're going to look like, outward pointing rays as well as concentric circles if you look at the poles. So that's why we call them polar. And you can tell we're still filling, right? This still fills 2D space. We just don't have this notion of a grid. Like the Cartesian coordinate system is like a grid on space. The polar coordinate system is kind of these sectors of space. Think about radar as well, if you've ever seen radar. So thinking about plotting these, I'm just going to go back to like a real dimensional system rather than jumping right into complex. Here I've drawn, this is my polar grid or polar sector of two-dimensional space, rather than the grid, which we saw in Cartesian, right? The grid I had kind of, given a bunch of vertical lines as well as a bunch of horizontal lines. That was the Cartesian coordinate system. It looked like that in the previous video. I've changed my lines to be circular now, as well as these outward pointing rays. And we can actually still talk about points in a polar coordinate system. Like this point 1 comma pi over 4, we can no longer think about this as the first entry 1. This is not left, right. And the pi over 4 is not up, down. But rather in a polar coordinate system, they refer to the radius of the point as well as the angle the point makes with the x-axis. So we're thinking back to like the unit circle. I mean, the unit circle is kind of sitting inside of here, right? It's right there on this particular image. So we're thinking about a radius and an angle with the x-axis. So how would I actually find that point? Well, we can get lucky with this radius one, and we can treat it the same as an x value, because we're going to run along the x-axis first, even though it's not actually an x value. It's a radial value. But if you think about it, any distance on the x-axis is some radial distance from the origin. So we will actually still treat it as the x value. In this case, when it says a radius of 1, we're going to move out one distance on the x-axis. And then now, remarking that pi over 4 is an angle, really counterclockwise, just like the rest of our angles, of pi over 4, we're going to jump up in an angle of pi over 4 from the x-axis. And this will be my point 1 comma pi over 4. And so you'll see that second amount I moved was really a curved amount, no longer a vertical amount the way it used to be in the Cartesian coordinate system world. So if we look at 2 pi comma pi, I'm going to go out 2 pi units in the x-axis. So 2 pi will get me to 6.28, and then I'm going to move up pi angle from this axis, and recall pi is exactly 180 degrees, and so that's going to pull me all the way over here. It's going to be 2 pi comma pi. And then finally, my last point, root 3, 3 pi over 2, I'm going to go out root 3, which recall is about 1.7 on the x-axis. And now I'm moving an angle measurement of 3 pi over 2, which is 270 degrees. So that's going to pull me around to here. So this will be root 3, 3 pi over 2. So that's how we want to think about the polar coordinate system as opposed to the Cartesian coordinate system. It's a radius and then an angle as opposed to just a left, right, and an up, down. So I've got, the points plotted in the book as well as exactly what I've just drawn out for you to give a good idea of how those work. We can do the same thing with the complex numbers. Keep in mind when we had Cartesian, let's say Cartesian 2D points, we had something like 1, 1, and then if we represented this as a complex number, we represented it as 1 plus I, because we were thinking about this as a movement along the real axis and this as a movement along the imaginary axis, which just happened to be a 90-degree rotation. When we're dealing with polar 2D points, we have this notion of a radius and a angle, and that can't really map into the same idea of just adding two complex numbers together. We'll see, it won't make sense right away, but we'll see that these have to get represented as the radius r, so in this case 1 times an exponential, so the Euler's exponential, e to the I times the angle pi over 4. And so we've got the radius here, and we have the angle up top here. Now, it's not going to make sense why that should be the way it looks in complex land right away, but we will eventually describe why that's the case. But for now, just think about it as the Cartesian, now just think about it as the polar complex numbers. These are complex numbers where you're taking some radius and you're multiplying by e to the I times some angle. The radius is allowed to be positive. The angle is allowed to be between 0 and 2 pi. Let's just jump up to here to explain why it would make sense for the radius to only be positive. Well, I can start here and I can go as far out in the positive x direction as I want. And then I can fill all of space just by moving any amount that I want to in some sort of arc. Right? Once I make it back to 2 pi, then I've come back to where I've started. So there's no reason we need negative radii or angle measures greater than 2 pi. So this formula, which is called Euler's formula, is actually the reason why we can represent all complex numbers as r e to the I theta. This is because it'll take us a few sections to eventually prove this, but it's because e to the I theta happens to be equal to cosine theta plus I sine theta. And if we think about these two terms as the x coordinate and the y coordinate, that's exactly the x and y coordinate of the unit circle. And if we turn around and multiply e by an r, we have a radius times the x coordinate and a radius times the y coordinate of the unit circle. And so that's actually what's happening when we write these polar complex numbers, is this e to the I theta is behaving like the unit circle for us, and the radius is kind of extending the unit circle out to whatever radius we want it to be. It'll take us a little while to prove it, though. So here I've described that all complex numbers of the form cosine theta plus I sine theta, which we just discovered was in fact e to the I theta, does compute the unit circle. What I've written out here is all of the terms for theta between 0 and pi over 3. That's kind of this arc of the unit circle. Between pi over 3 and 2 pi over 3 is this arc of the unit circle. 2 pi over 3 to pi is this arc of the unit circle. Pi to 4 pi over 3 is this arc of the unit circle. 4 pi over 3 to 5 pi over 3 is this arc of the unit circle. And I know it's a little hard to see, but 5 pi over 3 to 2 pi is this final arc of the unit circle. And so I'm just trying to stress that really cosine theta plus I sine theta, which is the same thing as e to the I theta, is the complex unit circle. And then if we multiply it by the radius, we're just stretching it larger if the radius is greater than 1, or stretching it smaller if the radius is less than 1. So now we can actually think about plotting polar complex points in 2 dimensions. So if I've been given maybe my complex point e to the I pi over 4, we should identify the radius here, even though it hasn't been explicitly shown. It's a radius of 1 because there's kind of an implicit multiplication by 1 in front of this term. So we've got a radius of 1 and an angle measurement of pi over 4. We're just going to go back to where we were before. This is the point e to the I pi over 4. If we think about the next point we have here, 2 pi e to the I pi, we've got a radius of 2 pi. So we're going to jump out to 2 pi, which is 6.2, and then an angle measurement of pi, which is 180 degrees. And that's going to pull us around over here. This is the complex point 2 pi e to the I pi. And then our final complex point is root 3 e to the 3 pi over 2. That says the radius is root 3, so we move out by 1.7, and then an angle measurement of 3 pi over 2. We're going to rotate this around 3 pi over 2 radians, and we end up here. This is root 3 e to the I 3 pi over 2. So that's how we think about these complex numbers written in a polar form with these exponentials on them. We just kind of extract the radius and the angle measurement out of them. Now I do have a remark here, which is telling us that negative radii and all values of angles are allowed. So you're going to see more values of a radius. Normally I say the radius is in this positive real line, so 0 to infinity, and I say that the angle measurement theta is just in 0 to 2 pi. But I really only say that because it's the minimum what you require to actually find every point in the 2-dimensional plane, but it's perfectly allowable that I give myself negative radii in every angle measurement. It's just that maybe, large angles wrap around extra times. For example, 4 pi, right? This is 2 pi angle measurements. 4 pi would take me back to where I started. Perfectly valid angle measurement. I've just wrapped around twice. And you can interpret a negative radius, right? The first radial direction we went in was this direction, and then we moved away from that direction, positive x-axis. A negative radius would send me, so I'll say negative r will send me to the left, and I'm still going to move counterclockwise. It's perfectly allowable. You just don't need it, so you're not going to have unique polar coordinates if you don't restrict your radius and angle to those values. Otherwise, you have non-uniqueness, which is sometimes confusing. Ambiguity is kind of the bane of mathematicians. Well, let's just get an example of -2√3 e to the negative I pi over 6. So this is where I've given myself a negative radius and, in fact, a negative pi over 6 angle measurement. If we look at that and we compare it, maybe the one I was just talking about, compare it to the positive 2√3 radius as well as an angle measurement of 5 pi over 6. If we think about plotting these, well, the negative 2√3 says I start at the origin but I move left, and then I have got this negative angle measurement as well. So negative angles are going to go clockwise rather than counterclockwise, so now I'm going to go clockwise by a pi over 6 amount, and I end up at this point. Whereas if I had the positive 2√3, that's going to send me in the positive x-axis direction, and then a positive angle measurement of 5 pi over 6, and I'm going to move in the counterclockwise direction around the circle and then end up 5 pi over 6. You end up at the same point. So you have this kind of non-uniqueness of polar representations if you allow the radius to go negative and if you allow theta to take on values outside of 0 to 2 pi. Perfectly allowable, just non-unique, and it's important to recognize that these 2 points can actually have different representations. Okay, so these operations are going to look insane. So just like with the Cartesian complex numbers, we can add, subtract, multiply, and divide polar complex numbers. And let's forget about the addition and the subtraction right away because they're just going to be intimidating. Really, let's talk about multiplication and division because that's kind of the point of these polar complex numbers. Remember how, and I'll mention this here, remember how multiplication by I is a 90-degree counterclockwise rotation. Yeah, and so when you think about rotations, polar coordinates are much more adapted to a rotational world, right? Circles and rotations are kind of the same thing. And so it turns out that multiplication in a polar world, so this is like r1 e to the I theta 1 and r2 e to the I theta 2, it is really well behaved, right? Because the radii, these are just kind of coefficients that are multiplied together, they end up multiplied together. And our power rules, remember, if the base of exponents is the same base, our power rule says all you have to do is add the exponents. So you have this really nice idea of multiplication in polar world where you just multiply the radii and you add the angles, right? So this is multiply radii and add angles. So polar is somehow like really well behaved in multiplication land, and in fact it's really well behaved in division land too, because you can think about division land here. If I'm dividing that complex number by the other complex number, it's really r1 divided by r2. The denominator exponential, well, exponents in the denominator are really just negative exponents in the numerator, and now we can just add those exponents together as negative theta 2 plus theta 1, also known as theta 1 minus theta 2. So you're just going to divide your radii for division and subtract the angles. And so they really are well behaved for multiplication and division. That's kind of why we even have them as mathematicians. Otherwise we would never work with these polar forms. But it's absolutely horrendous to add or divide these things. So we'll look at these really quick. We'll talk about this addition and subtraction really quick, but I would say don't ever do it. It's no mathematician's ever going to really ask you, except for maybe in exercises, because I can be mean. No mathematician's going to ask you to add polar complex numbers together. It's really not done very often. They were kind of developed to be multiplied together. But anyway, this is the formula for adding and subtracting them. And we'll just talk about the addition formula right away because, of course, it's the same thing as the subtraction formula up to taking that minus sign and including it on R2 and then just substituting every R2 in the addition formula with a minus sign. So we'll talk about this addition formula really quick. So the addition formula, what's actually going on here is we basically have, that's more or less is the magnitude of the complex number. That's a magnitude of the complex number. And so what you see here, r1 squared plus r2 squared and a square root, you really are recalculating the magnitude of a complex number there out front. Where does this 2r1 r2 cosine theta 1 minus theta 2 come from? Well, it's really a subject for linear algebra to talk about that. It's really talking about the inner product of two vectors and how much their magnitudes line up or cancel. What that inner term is doing. So we're not going to worry too much about it. For now, think about it as a formula. I did technically compute everything out in our proof below if you're particularly interested. And then we'll talk about this tan inverse up top. I have a little footnote here that says the inverse tangent terms and exponentials are actually the quote 2-argument arctangent function a tan 2. And that'll take you to a link that describes that. What this tan inverse function does is when it's 2-argumented, when it has a double argument, a tan 2, it takes the numerator here and it associates this to a y value in the xy plane, and it takes the denominator and it associates it to an x value in the xy plane. And then because you've got this y divided by x and you're taking tan inverse of y divided by x, what we're actually reproducing with this arctan here is this ends up being the angle, the theta, for which the point xy makes with the positive x-axis. But we're not really going to worry about this very much. It's really something I wanted to show was possible, but probably shouldn't be done. There's the lovely proof for that term. I did give examples. Let's go ahead and do it to see that, we can be done. It's not the worst thing in the world. So let's take the polar complex numbers root 2 e to the I pi over 4 and root 2 e to the I 3 pi over 4. We're going to add them together, at which point if we just follow the proposition, what do we have to do? We have to isolate r1 and r2, and we're going to take r1 squared, 2r1, r2, and r2 squared, but we also have to find theta 1 and theta 2, and we have to subtract them inside of cosine. So I'm going to go do that. We've got r1 squared, we've got r2 squared, and we have r1, r2 times 2 right there. And then finally we subtract our angles, so pi over 4 minus 3 pi over 4. If I simplify all those terms inside the square root, what do I end up with? Thankfully I have a cosine of negative pi over 2. Let's think about where that is on the unit circle. Negative pi over 2 means I'm coming down here. What is the x value there? Well, that's the point 0, negative 1. So thankfully that cosine value is 0. Everything drops out. I'm just left with root 4, also known as 2. So that's the kind of the new radius. Let's talk about this term over here. Where did that term come from? Well, if I jump all the way back up here, let's look at it. I've got r1 sine of theta 1, r2 sine of theta 2, r1 cosine theta 1, and r2 cosine theta 2. Let's jump back down. r1, there it is, sine of theta 1, there it is, r2, there it is, sine of theta 2, there it is, r1 cosine theta 1, r2 cosine theta 2. Let's figure out all these points. Well, pi over 4, 3 pi over 4, pi over 4, and 3 pi over 4. The cosine of 3 pi over 4 is negative, as can be seen, and the sine of 3 pi over 4 is positive. Now, I wrote them as ones right there, but that's because all of these were multiplied by root 2. Keep in mind the pi over 4, something like sine pi over 4, is actually 1 divided by root 2. So the fact that there's a root 2 up front, it's canceling with the root 2. So I have 1 plus 1 in the numerator, 1 minus 1 in the denominator. Here is where I'm referring to now, this arctan function, or the atan2 function, which is the special version of arctan, where I'm just associating the numerator to a y value, the denominator to an x value. And let's plot that point. Well, 2 comma 0, y value 2, x value 0. That's right there, 0 comma 2. And then I ask the angle with the x-axis. What is this angle? Well, that angle is pi over 2. And so I've actually replaced it with pi over 2. Even though I've divided by 0, that's kind of a no-no. We can still interpret that, as the numerator being a y value, the denominator being an x value, and then finding the angle. So that's how we simplify that. And I do describe, in some prose detail about how I found that pi over 2. Subtraction's the same, right? Subtraction, I'm just going to replace every case of the positive root 2 for r2 with now a negative root 2. So it's going to give me a negative right there. It would give me a negative right here, but it's squared, so it doesn't matter. And then up here, these both become negative, and now my numerator has turned into 0. My denominator's turned into 2. So let's think about where this point is on the xy plane. Well, the point 0 for y and 2 for x is right here at the point 2, 0. And what angle does that make with the x-axis? Well, that's an angle. Theta is 0. And so I've replaced the 0 there. E to the I times 0. We still have this idea that anything to the 0 power is equal to 1. So we can just call this number 2. And some prose to talk about where I came out with the angle measurement of 0. And then we get to the easy ones, because that's the whole point of polar complex numbers, is to multiply and divide. So if I'm multiplying polar complex numbers, I'm just multiplying the radii. I get 2 copies of root 2, which gives me 2. And I'm going to add the angles. If I add pi over 4 to 3 pi over 4, I just get 4 pi over 4, also known as pi. Also, if I divide, then I'm just dividing my radii. They cancel, and I get a radius of 1 in the end. And if I take the upper angle and I subtract the lower angle, that's pi over 4 minus 3 pi over 4, also known as negative 2 pi over 4, or negative pi over 2. And this is a perfectly valid answer. Except I personally do like restricting the values of my angles to be, 0 to 2 pi. So I'm going to say, well, what is the angle negative pi over 2, that's right over here, right? Negative pi over 2. In terms of a positive angle measurement, that is, 3 pi over 2, right? And so I've replaced my pi over 2 with 3 pi over 2. So just as before, we do often use z as kind of the generic complex variable instead of r e to the I theta. So you're going to see that thrown around a lot. And we have the complex conjugate just as before, but we can apply now our complex conjugate. Remember before it had something like x plus I y, and we would take a conjugate, we would get x minus I y, because we replace I with negative I. We can do this in polar form as well. We still replace I with negative I. So it's just that the negative just pops right through. We have r e to the minus I theta. We can look at an example of this. Let's suppose we have root 2 e to the I pi over 4, or root 2 e to the I 3 pi over 4. Take a complex conjugate, we're just putting a negative sign in for our i's. If you want, you can convert to positive angle measurements again, but you totally do not have to, and you can be content with your negative angle measurements there. The norm works the exact same way, but it's actually really well behaved in terms of polar complex numbers. Because let's think about it. What is the radius of a polar complex number? Well, the radius of a polar complex number, if I have that point there, the radius, you can think about it as how far to the right did I travel and then up, but you can also think about the radius just as how far away it is from the origin. And so we see that the norm of a polar complex number is precisely the radius, and that's really nice to see, as long as this was written as a non-negative number right away. You can just immediately extract the radius as the norm or the magnitude. So that's actually one more word you can use if you want to for a complex number would be the radius. So let's look at an example of those norms and magnitudes. Well, they're pretty easy to tell, right? Because we've got a root 2 there, a root 2 there. I've gone through all the work to actually calculate these, but let's think about it. It is the radius, so if I have the root 2 of z, root 2, and I have a root 2 on w, root 2. Real and imaginary parts get a little bit trickier, but let's think about going back to Euler's formula. E to the I theta is cosine theta plus I sine theta. This is actually written in x plus I y form. And if we think about it, what was the real part of x plus I y? Well, it was just x. So the real part of e to the I theta is cosine theta. The real part of r, e to the I theta is r cosine theta. Same idea with the imaginary part. Imaginary part of x plus I y is just y. If we look at e to the I theta, that's I sine theta. And so r e to the I theta is just coming through as r sine theta. These still apply, but we don't have to worry about them the same way. Just think about the real part of a polar complex number is r cosine theta. The imaginary part of a polar complex number is r sine theta. We can look at the examples of the real and imaginary parts. We're just going to immediately think about that as r cosine theta. So the radius root 2 cosine theta. Theta was pi over 4. Turns out the real part is going to be 1. If we look at the real part of this w as well, the real part of e to the I 3 pi over 4, we've got 2 cosine 3 pi over 4. That's going to give me negative 1. Same idea with the imaginary, where I'm going to have the imaginary is just the radius times sine, which will give me 1 in the first case. Imaginary part is the radius times sine, which will give me 1 in the second case. Let's go back to graphing these really quick. So what are my 2 points that I'm looking at? It's going to make sense if I graph these. My 2 points are root 2 e to the I pi over 4. So I'm going to jump out to the right by root 2 and then up by pi over 4. There's my first point, root 2 e to the I pi over 4. And my second point is root 2, there's supposed to be 3 there, e to the I 3 pi over 4 is the same amount to the right, but then I'm jumping out over to here, root 2 e to the I 3 pi over 4. If we think about the real and imaginary parts here, well, the real part is just how far to the right are these points? Well, the first point is 1 unit to the right. The second point is 1 unit to the left, also known as negative 1 units to the right. And then the imaginary parts is how tall are they? Well, they're both 1 unit above the x-axis, so the imaginary parts are just giving me 1 for both of those points. It does make sense either way you like to think about it. And then the final subsection, now that we've seen the polar representations, kind of the whole point of this is that they're the same numbers. The Cartesian polar representations are the exact same thing. It's 2 sides of the same coin. Different representations. Polar are really meant for multiplication and division, or to visualize rotating complex numbers. The point of complex numbers is rotation, and so that's why the polar representations are useful. The Cartesian representations are useful every time you actually want to add them or subtract them. And you can get away with multiplying and dividing the Cartesian ones as well. So in general, the Cartesian ones are maybe a little more well-behaved, but it's good to keep in mind the polar ones because they're always going to be there if you want them. So with that said, I've got this proposition, which I call transforming Cartesian to polar and vice versa. And I'm going to start to write my points using a subscript POL and a subscript CART for Cartesian and polar respectively, just so that it's quite clear which coordinate system a specific point is in. A lot of books won't do this, and it's frustrating that you have to use your context clues to figure it out. But for the rest of this book, I will be using that. So you can feel good about always seeing a subscript cart or a subscript pole if I'm in one or the other coordinate system. But what's the point of this proposition? Well, the point is that you can actually translate this point written in Cartesian into this point written in polar using the following, it's called a transformation. So using the following coordinate transformation, the r, so the r in our output up here, this r will be written as root x squared plus y squared. And the theta in this output will be written as, well, this is exactly the a tan 2 function actually, the two double pointed inverse tangent function. So you think about theta, you're just asking what angle with the x-axis does the point xy make. But you can think about it as if you plug it into your calculator, it's the inverse tangent of y over x as long as x is positive. It's the inverse tangent of y over x plus pi as long as x is negative. And in fact, it's just the sine of y times pi over 2 if x is equal to 0. But otherwise, if you're worried about this, just plot and find the angle with the x-axis. That's the way I always do it. I don't even plug it into my calculator. It's easier to just plot and find the angle with the x-axis. And so really I could have written this as, rather than writing it as r comma theta, you could write it as root x squared plus y squared comma tan inverse y over x, possibly plus pi for that second case. But that would be the polar representation of our original point x comma y. And you can actually do the reverse. That's what I say here. So starting with r theta in polar, you can end up with xy in Cartesian. In this case, the x is going to be equal to r cosine of theta, and the y is going to be equal to r sine of theta. There's no ambiguity about what your output's going to be in this case. And so you can just be immediately happy by saying this xy Cartesian is just r cosine theta, comma r sine theta, cart. So you just go ahead and produce it. You can do the same thing with the complex polar and Cartesian coordinates, right? Because everything I've written up here is really the real polar and Cartesian. So in complex world, our Cartesian coordinates look like x plus iy, and our polar coordinates look like r e to the I theta. Well, r is the same thing as before. It's root x squared plus y squared. And the theta, right, so e to the I comes along for the ride, but theta is the same as before. This is tan inverse of y over x plus a b plus pi. And then you can do the reverse again. Suppose you start with r e to the I theta and you want to write it as x plus iy in the complex numbers. Well, x is going to be r cosine theta, y is going to be r sine theta. So this looks like r cosine theta plus I r sine theta. And so that's how you represent, starting from a polar coordinate complex number r e to the I theta. Suppose you wanted to convert it into the Cartesian complex number. That's the way you would do it. So let's look at an example of actually performing these transformations. Suppose I have this point negative root 3 comma 1 in Cartesian land, and I want to write that in polar land. Well, what I'm going to do is I'm going to use these transformations. I'm going to plug the values negative 3 comma 1 in. So negative 3, of course, is the x coordinate, 1 is the y coordinate. I'm just going to go ahead and plug it in. So if I look at, so let's actually do an example of one of these. If I want to, or really two of these, if I have 2 points, 1, 1 in Cartesian land and negative root 3, 1 in Cartesian land, and suppose I want to write them as some r theta in polar land and r theta in polar land. I can do that following my transformation maps. And what do I do for that? Well, I take this 1 and I plug it in for x. I take this 1 and I plug it in for y, and I end up getting root 2 for that first case. And in the second case, I'm going to take negative root 3. I'm going to plug that in for x. Negative root 3, there it is. And I'm going to plug 1 in for y, 1 in for y, and I end up with 2 for my second radius. And in terms of theta, well, I'm going to follow this particular map. In the first case, 1 and 1, well, the x value, 1 is positive, so I'm just going to follow this. And when I follow that, I have tan inverse of 1 divided by 1, which is tan inverse of 1. Plug that into the calculator, you'll get pi over 4. And so in my first case, I've calculated the radius and the angle, and I can just write it as root 2 pi over 4. Keep in mind, this was the first case, equals 1, 1 in Cartesian. They're two sides of the same coin. If I want to do that with the second case, my negative root 3, 1, well, my theta, let's think about negative root 3. Negative root 3, x is negative, which means I'm going to have to add pi to inverse tangent. So I go ahead and do it. I calculate inverse tangent of negative 1 over root 3, and then I go ahead and add pi. So my calculator tells me negative 1 over root 3 gives me negative pi over 6, but I'm going to add pi because the x value is negative. I end up with 5 pi over 6. So that means that my polar representation of this point, negative root 3 comma 1, is 2 comma 5 pi over 6. You can do the same thing with complex points, right? They just look a little different. So 1 plus I is my complex point. Negative 3, or root 3 plus I is a different complex point. And you go through the same process, and you still get root 2 as your radius. You still get pi over 4 as your angle measurement, but we just kind of represent these complex numbers differently. The radius sits out front, and we have e to the I theta as our angle. And so this is going to be equivalent to 1 plus I. They're the same thing. And then doing the same thing with our point, a complex version of the point. Negative root 3 plus I, the radius still becomes 2, and the angle still becomes 5 pi over 6. We just want to think about writing our complex version as r e to the I theta, and this is still equal to the complex point, negative root 3 plus I. So two sides of the same coin. For any of them, it's nice to know that you can transfer back and forth. Similarly, if we start with polar coordinates, let's say we started with polar coordinates in R2, we can use the r cosine theta and r sine theta for x and y respectively to send maybe our first polar coordinate, root 2 pi over 4, send it to an x and a y. If we plug root 2 in, right? For r, root 2 in for r, and pi over 4 in for theta, what do we get? Well, we get exactly 1 for x. If we plug in root 2 for y and pi over 4 for theta, then we end up with root 2 sine pi over 4. Root 2 times 1 over root 2, y is going to be 1. And so once again, two sides of the same coin. This is 1, 1 in Cartesian. If I do that with my second point, which is 2 comma 5 pi over 6 in polar, I plug the 2 in for r in the x-coordinate, and I plug 5 pi over 6 in for theta inside of cosine, and that simplifies to negative root 3. If I plug the 2 in for the radius for the y-coordinate, 5 pi over 6 in for the angle measurement in the y-coordinate, I end up with 2 times 1 half, I end up with 1. So my Cartesian point is negative root 3 comma 1. And that's going to be the equivalent of this point, 2 comma 5 pi over 6 in polar. And finally, we can do it yet one more time in the complex versions. We can say root 2 e to the I pi over 4, that's a complex polar coordinate. We can rewrite it by plugging in the radius, root 2 in for the radius in x being r cosine theta, and pi over 4 into the angle measurement for x equals r cosine theta, and we find out that x is equal to 1. Same idea with y. Y is going to be equal to r, which in this case is root 2, times sine of the angle. The angle in this case is pi over 4. We simplify that and we get y is equal to 1. And so, kind of once again, two sides of the same coin. This root 2 e to the I pi over 4 is the same complex number as 1 plus I. And finally, 2 e to the I 5 pi over 6. We're going to plug in the radius, which is 2 for the x-coordinate. There's the radius in the x-coordinate. Cosine 5 pi over 6, because 5 pi over 6 is your angle measurement here. Simplify that, we get that the x-coordinate is negative 3, and the y-coordinate will still be 2 from the radius here. Sine 5 pi over 6, because 5 pi over 6 is our angle measurement. Simplify that, and we get 1 for the y-coordinate, which says, this is x plus I, y in terms of Cartesian complex numbers. So we have negative 3 plus 1 times I is the Cartesian complex number representation of 2 e to the I 5 pi over 6. Finally, I do have one brief corollary, which says there's a different representation of sine and cosine, which does show up every now and then to be useful. Sine of theta can be represented as e to the I theta minus e to the minus I theta over 2I, and that's just because it has to be the imaginary part of e to the I theta from, Euler's formula, cosine theta plus I sine theta. It has to be the imaginary part here. And then similarly, cosine has to be the real part here. So we calculate the real part as, z plus z conjugate over 2. And you just have this lovely representation of both the sine and cosine functions. Why is it actually useful to represent the sine and cosine functions that way? Well, I actually have this brief proof of sum of proposition 0.2.13. These are actually the trig identities. So the fact that it's easier to prove trig identities if you represent sine and cosine as kind of this combination of complex exponentials. You immediately recover a lot of the trig identities. I'm not going to go through all of these, but you just work through, here, for example, is the sum of angles formula. If you work through the foiling of all of these complex exponents and use your exponent rules, a lot of things cancel, and what you end up with is exactly sine alpha plus beta. In terms of the complex exponentials. And so it really simplifies the proofs of these trig identities to represent sine and cosine as complex numbers. And then I make one final statement, which is why should we even use polar form as opposed to Cartesian form? And we're going to see this periodically through the semester. Polar form is really written well for circles. If we need to do calculus with circles, which can happen, right? If you're calculating the volume of a soda can, there's a natural circle coordinate system to the soda can, or even on the surface of the Earth, for example. So if you're doing any calculus with naturally circular objects rather than with square-edged objects, I think when we build buildings, we build most buildings with square edges, good for us. But if you're talking about physical forces, there's a reason the Earth is a sphere. It's because gravity is spherically symmetric when it exerts its force, and so to represent some physical laws with a lot of forces, they act in circular directions. And so calculus with circles actually reduces to kind of an easier calculus if you use a polar form. So I just wanted to make that clear at the end here. That's where we're headed in terms of our calculus. And so I will see you in the next video for functions, inverses, and equations.